Okay, so can somebody remind me what the basic idea of the Cauchy integral formula was? First off, what was the Cauchy integral formula? Yeah, what was it? You can ignore the hypotheses if you want for a minute, and just tell me what the core idea of the theorem was. Yeah.
The ideas with the actual
formula? Well, the formula. Because
I
mean, if you're just telling me the formula, you're not telling me the whole theorem, right? You're just telling me what the computation at the end is.
Okay. F of W equals 1 over 2 pi I integral over C, and I will not say what C is. Is it F of Z over W minus Z dW? What am I doing? Z minus W. Oh, sorry about that.
Okay. All right. Oh, yeah, it's easy.
Totally.
Okay, so the picture that you should have in mind here is that you have some domain. So that is the correct formula. Now, what's the idea of the formula? What are you doing with this? Yeah? Yeah, so you imagine that C is given to you by some function gamma of t. So you parameterize the boundary. And the idea is that as you crawl around the boundary, that you can recover the value of the function anywhere in the interior, right? So this is one of the main ideas of functional or of complex analysis, is that if you have some point W in the interior, then the z's that occur in this equation, which are gamma of t's, as you crawl around the boundary, that you get the values of the function in the interior, right? So that's sort of a core idea of complex analysis. Yeah.
Does it need to be closed?
Well, okay, that's a good question. So the answer is if it's not closed in the sense that it runs off to, okay, so yes, right? So if you just had a chunk that was like some chunk, what you could do is a lot of times the strategy there is you complete the curve with something that's easy to compute, calculate on the closed curve, and then come back to the value there. But yeah, yep.
What is closed on a path through point infinity?
Conformally mapped to a bounded set, and then the formula applies. Right? I mean, there are conditions that need to be added to this about what sort of boundary you have. So generally, you have to assume things to make this work, like the boundary is nice enough.
Wait, if I have a region and I want to know the value of the function not on that region, can I do a conformal map to get everything outside the region?
As long as you stay away from places where the function isn't analytic, yeah. Right, so like this, generally once you combine this idea with conformal maps, you really extend your ability to calculate the values of functions from looking at their values on the outside, on the curves on the inside. And so the sort of basic set of assumptions here is that F is analytic, C is nice. Usually what we mean by nice is that you can parameterize it with a continuous function or a piecewise continuous function. So nice, it's like what's simple, piecewise, continuous, and closed. Something like that. And the basic theme of this was the idea that the interior values are determined by the boundary values. Okay. Now, I'd be really impressed if anybody could remember the Gauss mean value theorem. Not the mean value theorem from 412. Remember, last quarter we said that this mean value theorem for us was different. It had something to do with the average value of the function. Yeah.
The value at a point is the average of the values on the circle.
Yeah. So the circle, instead of the picture being this, the idea is that if you started in some domain, say A, and now you pick a point W in the interior, that you can find a little circle around W of radius R, so that this circle is parameterized. This is something like W plus RE to the IT is the curve that you build now. So you have some circle that goes around the point.
What's the word next to piecewise?
I'm sorry, CTS, which is just supposed to be continuous. And the point of the Gauss mean value theorem is that this gets you actually a real valued equation, right? So here I think, let's see if I remember how to write this down. It's 1 f of f at w is equal to 1 over 2 pi times the integral from 0 to 2 pi of f evaluated at,
Should I Google it?
what's that? Yeah, I mean, I could just look it up. It's more fun to sit here and try to guess what it was from memory, but that's probably not so amusing for you guys. So
I feel like it's very similar.
it's just, I mean, all you're doing is just taking that and restricting it to. You're just doing a path integral around this. It's just a path integral around the circle, but it has a specific form where you mod out with the. So yeah, it's exactly what I was going to write, which is f of z naught, or w I guess in this case, plus r e to the I t dt. T, that's right, the angle. So essentially you parameterize like this, so that you think about this as a circle being parameterized by the angle, you travel around, and this is saying that the value of the function at w can be recovered with this real valued integral where you're just tracing out this circle, right? So it's that picture, but even better because now you have circles involved. Yep.
If I think about real integration, and we're doing polar integrals for real, like one variable integration, don't you have to like square the radius component because as you move away from your point where you're centered around, the quantity that you're integrating gets stretched out by some factor of r or something like that?
I mean, okay, so if you actually go back at the derivation of this formula, that's actually canceled out by the fact that it comes from this formula and an r appears in the denominator as well. So there's an r in the denominator and r in the numerator that cancel each other. So that scaling factor is already taken care of.
Cool.
So if you substitute this parameterization into that, this is what falls out.
Okay, I think
Yeah. Okay, so now, armed with this, I mean, this is all driven by the Cauchy integral formula, right? This idea of the big theme being that interior values are determined by boundary values. Yep.
So is this like an existence statement that such an R exists, or that?
It's any R that fits where the circle sits inside the, if you could, any circle that you put inside of A, you always recover the value of W by tracing out the circle. This is actually where the maximum modulo principle sort of comes from, is the idea that as you go, the circle gets bigger, but you still are equal to the same value in the center. It kind of gives you this weird sort of oscillation around the oscillation. Yeah, no, I mean, you've got control over the way the function grows because it always has to be equal to the same thing. So as long as the circle fits inside the domain, you're always going to be integrating to the average value. Yep.
So does that mean if I know what a harmonic function does on some simple closed continuous curve, I know what it does everywhere?
In fact, you just anticipated the next thing I was going to say. Yes, the answer is correct. Because that's actually what this is all supposed to motivate is, there's a famous problem in mathematics that motivates the study of harmonic functions and the Laplacian in physics called the Dirichlet problem. If you want to say Dirichlet, you can say Dirichlet. You can say Dirichlet. All right, so the Dirichlet problem, see now you've got me here, says the following. So this is what it requires. Given a region, let's say in R2 even, so given a region in R2, this is going to be a question about harmonic functions. Given a region in R2, we'll call it A, with a simple, well actually with boundary, I guess we'll call it C, that is bounded, simple, closed, find a harmonic function. Okay, that's just the setup so far. So you're given a region in R. Here's the boundary C. A lives inside of it. Now, I'm going to tell you what the boundary values are. So I give you a set of boundary values. I say you're given a continuous function, doesn't have to be continuous, but for now let's assume continuous. A continuous function u, we'll even call it u naught on C. So that's the thing you're given. That's essentially I'm saying I tell you what the values of the function of some function are on C. So that's known. So you know the boundary values everywhere. So this is all given. Find a harmonic function on A that extends to the boundary by continuity, that agrees with the given function on the boundary. So I'm going to resort this slightly because I wrote it down low. So what you are given is the domain A, the boundary C, the boundary values u naught, and what you want to find is a harmonic function u of x and y on A. So what does it mean to be harmonic? Right, so that symbol means uxx plus uyy is equal to 0. It's the definition of harmonic. So you're looking for a solution to this differential equation on the interior that when you push it to the boundary that you recover those values that you were given. So that u is equal to u naught on C. So the name of this question is the Dirichlet problem. This is one of the sort of core problems that shows up in one of the earliest, actually, examples of a partial differential equation that was thought about by mathematicians and physicists. If you want motivation for where this comes from, sort of where this came up when Fourier and Laplace were thinking about this problem. Yep.
Is there any conditions we know about the behavior of the function on A? Like there's not a singularity?
Well, continuous, right? So, oh, you mean on A itself?
Yeah.
I mean, so if I say something is harmonic, remember it has to be the real part of an analytic function, which means it can't have any singularities, right? So this is going to turn out to be equivalent to finding an analytic function on A, right? And that's actually going to be our link with complex analysis and why complex analysis is useful. Is asking for a harmonic function is the same as asking for an analytic function. If I can find one, I can find the other. So the original sort of setup for this, the original motivation, comes from something called the heat equation. And the heat equation in simplest form is ut is equal to Laplacian of u, or if you like, ut is equal to uxx plus uyy. It's a relationship between the way that you think about u in this context. When you're thinking about heat, you're thinking about A as being some sort of plate of material sitting in space, and the function u is the distribution of heat energy across the plate. And the time derivative is a way of measuring how the heat is flowing through the plate as time evolves, and this is giving you some measure of the directions in which the heat is flowing, right? So you can think about this as somehow describing, like as you look around through here, right, as you sort of, where your concavity is, right? This is a measure of concavity. So it's a measure of like acceleration, or like what direction the heat is actually flowing out of that point. And the heat equation is just the observation that these quantities are related to each other. So where does the Laplacian come from? Well, suppose that you don't actually care about about this. You just say, oh well, what if we consider the case that 0 is equal to this? What if the steady state solution is sorry, I don't want to devolve too much into talking about differential equations here, but the idea is that if you're not concerned about solutions that depend on time, you just drop that term. And what you're looking at is what are called equilibrium solutions to the equation. If you think about if everyone here probably took 242 or 244, you solve a differential equation, you've got to find the homogeneous piece of the differential equation. This is essentially finding the homogeneous pieces of the heat equation. And the study of this equation and its solutions is called potential theory. But this is why they originally were doing this, right? So solutions to this turn out to be the homogeneous solutions to the heat equation, and then I don't have no idea where the name harmonic originally came from, but they were important enough to give them their own name, so I call them harmonic. Okay. So that's why we're doing what we're doing. So you should notice here, the Dirichlet problem and the really seems an awful lot like it's going to link up with all that stuff about Cauchy's integral formula and the Gauss's mean value theorem, because it's the same question. It's a question of, I've prescribed you some values, and this time I prescribed you the values on the boundary. Can you rebuild what happened in the interior by doing that? And it turns out to be the case that this question has a rather famous answer in the case where the region is a disk. And so the solution to the Dirichlet problem when the region is a disk is called the Poisson integral formula, Poisson's theorem, Poisson representation. So if the region A is a disk, so that C is a circle, then you get a solution. And it looks like, let's see. Okay. Oh, and I guess I should say here, U. Is defined and continuous on C, then you write down, I guess we can assume, because this is a disk, we might as well assume it's centered at 0, because I can just translate back to the origin, right? So picture here is you've got 0 now, there's some radius r, there's C out here, which is the circle that surrounds it. Well, if I slid the disk back to 0, there's no reason not to just assume the radius was 1, because I can just scale my solution. So might as well work on the unit. Well, right? This is the sort of idea of conformal maps. It's like every disk is the same. You just like translate and shrink, right? And if you solve it here and you want to go back to the original set, you just untranslate and blow it back up again. So the first idea is we might as well work on the unit disk. So I'm even going to go so far as to write the heinous expression W log here, which I did not know what this meant until my 4th year of math. I was like, why do people write W log all over the place? So this just means without loss of generality. Yeah, W log. It's terrible. We might as well assume that A is the unit disk. So that's the set Z where the modulus of Z is less than 1, and C is equal to the unit circle. Z, so the modulus of Z is equal to 1. And in that case, if rho is, oh dude, that's bastard, sorry. Does he really? Okay, you know what? I'm just going to keep doing it this way. If rho is less than 1, then U of Z, oh my god, there's not going to be enough room for this monstrosity. Okay, so I'm going to write down this formula, and it's going to look mysterious, and then we're going to try to figure out what the hell it comes from. U of Z is equal to 1 over 2 pi times the integral from 0 to 2 pi of U of R, E, not R, rho, E to the I phi times rho minus absolute Z squared over R E to the I phi minus Z squared. I have completely botched this. I hope you guys will forgive me for being up all night with my kids. I can't even read my own notes. So 1 second. Let me get this formula correct. I can record myself being exhausted for all posterity. So what I'm going to do is I'm going to write down an equation that tells me how to reconstruct the value of this function on the interior from the exterior. And I spent a lot of time trying to make sure this was smooth. Stupid. Okay, where does he actually do this? Okay, yep. So let's write this down. Okay. So I will do this correctly this time. I apologize for your notes. I'm going to write this the way it came up in the book. Your notes can forgive me later, and hopefully you guys will too. So let me write down the formula. And then we'll talk about where it comes from. This is used all the time in computation. So we're going to work with the disk centered at 0, radius r, so I don't have to try to interpret the formula. Then, for rho less than r, you get u of rho e to the I phi is equal to r squared minus rho squared over 2 pi times the integral from 0 to 2 pi of u r e to the I phi r squared minus 2r rho. I don't know why he writes it in this form, but I'm just trying to get it correct. Rho squared d theta. Or u of z, it is, but it's not as bad as it looks. 1 over 2 pi, it's not really. U r e to the I phi theta of r squared minus mod z squared over r e to the I theta minus z squared theta. Now, this is not something anybody ever remembers off the top of their head, right? You just don't remember this. What do these formulas, I mean, so every time you want to use this, you just punch it into a computer, which actually computers do use this formula, or you just look it up. The point here is that I want to think about what this actually means. How we get to a formula like this. We're not going to prove it, but I want to illustrate that the method that shows up from Cauchy's integral formula and the mean value theorem give you these. So what you're doing here, you can see that you're tracing around some circle, right? In this formula is the picture that you have some disk d radius centered at 0 and of radius r. And what you're saying is not that you're getting the formula out. So this is a slight extension of those ideas, because here what we're saying is if you give me some circle inside that circle, so you give me some circle inside, this is the thing that has radius rho, so that distance is rho, so you've got a circle inside that circle, that you can recover the values of any point along that circle at the point theta by integrating a function that is, again, around the outside circle. This is around the outside. R e to the I theta means that you're tracing the outside function of the circle to get the values on this inside circle. Right? Which means that if you can imagine that you could take this formula and you could just let rho run from 0 all the way out to r, and you're going to sort of fill out the circle with all these values in the interior. Does that make sense? Hopefully. So why does it look so bad? Well, basically you pick a point, and then you use a Mobius transform to slide that point to 0. And then you apply the mean value theorem, and then you un-Mobius transform to get back to where you started. So this looks so bad because the method of solution, if I say to myself, oh, I would like to have the boundary mapped to the, I actually want to figure out, given this outside disk with radius r, which is my C, the boundary of the region, and I pick some point here, which is rho e to the I phi. Gauss's mean value theorem says that the point has to be in the middle of the circle to recover the value at the point, right? So the Gauss mean value theorem requires that you're at the middle. That point's not in the middle. So what you do is you do a linear fractional transform that keeps this disk at the same rate. You can do that because you can map disks to disks, preserving the boundary. So you apply a linear fractional transform that gives you a picture that looks like this, where this is still the same circle of radius r, but now you've got sort of T of rho e to the IV sitting at the middle. So you transform the problem to one where that point gets sent to the middle of the disk. Then you apply Gauss's mean value theorem to recover the value by integrating in the outside, and then you go backwards to the original picture. So it's like you apply a linear fractional transform, you solve this using Gauss's mean value theorem, and then you take that picture and you put it back the way it was when you started. So now you put this point back. And this is what it looks like when you apply a Mobius transform and then undo the application of the Mobius transform. Yep.
So
Or linear fractional transform.
are those C's the same and we're like reshuffling the inside
Yes.
points?
Yeah. So it's an automorphism of the disk. Yep.
And then when you integrate around the disk, you get the value at the point.
Center.
And they're the same disk.
They're not. What do you mean the same disk?
They're the same boundary values.
Yeah. No. Okay. So you've changed the boundary values
Okay,
when you
that's
do
what
that. But the point is that it doesn't matter how you changed it because the mean value theorem says that doesn't matter. You just continue to integrate around. You've applied the linear transform over here to get new boundary values. But as soon as you do that, you've recovered the value at the transform. So then you just invert it and you get whatever that value must have been to. It's like essentially like the linear fractional transform is somehow preserving the structure of the boundary. It's not identical. The values are transformed at the boundary when you do that, but it's in an invertible way. So you transform the entire problem, including what happened at the boundary.
Well, it needs to be in a predictable way because otherwise the interval isn't work.
Yeah, but that's the Mobius transform is invertible, right? So you as soon as you write a Mobius transform down, you can always just flip it to go the other direction because it's an automorphism. Yep.
So the Mobius transform is what that one is called that does the.
Yeah, this is my bad. I'm tired, and so language is bleeding together here. So I'm not trying to confuse anybody. The other common name for linear fractional transform that you might see is Mobius transform. And so I'm sorry for letting different language from different classes bleed into itself. I'm not trying to be confusing with that. So Mobius transforms and linear fractional transforms are the same thing. But this is one of the big applications of, yeah.
Why is the top one a mess and the bottom one makes sense?
Might as what?
Okay, the two formulas, the way you explained it, like that explains the bottom formula. The top formula is like.
So this is called the real form. And this is the complex form. It's just that basically if you multiply out this thing and pull it together and substitute out the cosines, you end up with complex exponentials and you can just suck everything back in together again. These are just computationally equal to each other.
Okay.
Right? Because
we only like the bottom one.
What's that?
We only like.
Yeah, I mean the thing is that like in practice, this is the one that engineers use because they don't if you're working as an engineer and you think there's no such thing as complex analysis, I just want to use the tools. You can do harmonic function theory without ever referring to complex analysis. Right? It's got complex analysis running around in the background, but you never actually have to see it ever. Right? You can do everything that there is to know about harmonic function theory in the sort of basic setting without knowing that there is a complex version of this and the reason this works. So what's the perspective? That's a good question. Why does this work from the perspective of somebody who doesn't know anything about complex variables?
Because it said so in the textbook.
Yes, but there's a reason why that holds. There's a theorem that drives all of
Very
this.
smart.
Well, there's a specific theorem that says something about the behavior of vector fields on the interior and exterior of the domain.
Extension theory.
No, that tells us how to get from a real value function to a complex value function.
So how do you go back?
What's the most famous theorem there is that relates the behavior of a function on the inside of its domain to the behavior on the boundary? It's like Stokes' theorem or Green's theorem, right? The entire Gauss's theorem, this entire family of things that most people would call Green's theorem. Actually, really, it's all Gauss's theorem, and then there's special cases. But Green's theorem and Stokes' theorem give you ways of looking at the behavior of a function on the interior of a domain and relating it to its behavior on the outside of the domain. Right? In fact, we can write down what it says. So that is, let's look at this version of it. So we'll write down the divergence version of it. But it's an entire set of theorems that have this sort of form, right? So you have a domain A, and you've got some gamma that's describing how you're traveling around the outside. And then you have this thing that says that the integral, so I'll write down this thing and see if you can interpret it, around gamma of capital X dot n ds, that should jar some memories, is equal to the integral of the divergence of x. Yeah, this is going to go like this. It's the dx dy. Now, does anything about complex functions appear anywhere in that theorem? No. X here is supposed to be some vector field, right? So x, you can think of as being a sort of an x, sorry, a u, whatever. It's a vector field on A. Maybe you would call it, I don't know, u1 of x and y, u2 of x and y. Right? It's got vector field components. And the idea is that if you understand how this thing is acting at the boundary, so n here is supposed to be a normal vector to the boundary of the curve, that you're saying if you integrate over the interior, so the divergence is a scalar thing, right? So you calculate that divergence, you get this sort of scalar quantity that you integrate in the interior of the set, that's the same as integrating this sort of dot product function on the boundary. So this is another sort of class of theorems where you've got relationship between some function on the boundary of the region and a function on the interior of the region. Okay?
So only for conservative vector fields.
Yes. That's fortunate though, because conservative vector fields are secretly running around in the background of both harmonic functions and analytic functions, right? So these theorems hold for conservative vector fields, but conservative vector fields are the core thing that makes complex analysis work. We saw that when we built the Cauchy integral formula from Green's theorem. Okay. So, yeah, so that's kind of the deal here, is that like if you're doing harmonic function theory and you don't know complex analysis, you're essentially using the study of conservative vector fields to do it all. But you can sort of leverage the fact that complex analysis has this extra tool set to sit on top of that. And if you remember, the reason why complex analysis and harmonic analysis are linked is if you have f of z, which is f of x plus iy, which is u of xy plus I times v of xy, if this function is analytic, then these functions are harmonic. So the study of harmonic functions, thinking about conservative vector fields, is the same as the study of analytic functions. So here you have conservative vector fields in Laplace's equation. Here you have the Cauchy-Riemann equations. They're essentially equivalent to each other. So you have this perspective shift where you can go back and forth. Okay, so that's sort of the big thematic connection between these things. I will give a more clear write-up of why the Poisson integral formula is true, but that's basically, it's a whole lot of algebraic nonsense that really boils down to, you have this setting, you Mobius transform the disk, but when you learn this, usually you don't know about linear fractional transforms, right? So you do a linear fractional transform of the disk, but you don't know that yet, so they just tell you what the transform is. And then you apply the Gauss's mean value theorem, and then you undo it. And this is the result of whatever, the big nasty integral. So don't remember that. I mean, do remember the fact that it's essentially called, Poisson in French is fish, right? So it's the fish theorem.
We've had the second professor say that
Yeah. Today?
today.
Oh, man, I save up my fish jokes.
It's like 10 a.m.
I've had the rug pulled out from me. That's like, oh my gosh, like somebody woke up this morning at 7 o'clock, was like, I'm gonna make a joke about fish.
That's exactly how I felt it was.
Okay, so what's the next most, so what this means essentially, what I want you to think here is, what this means is that the Dirichlet problem is a well understood problem. And now, if you couple the Dirichlet problem with the observation that we know now what linear fractional transforms are, that means even though the Poisson integral formula only tells us what to do on disks, we can now work on anything conformally equivalent to a disk, because we can just transform the domain into a disk, solve the problem, and then transform the solution back to the original domain. Right? So the idea is, once you couple the idea with the fact that, oh, well, if I have a setup now where I've got some domain, general domain A, and its boundary is C, and I know U on C is given and continuous, as long as this is a bounded, simply connected, or sorry, not bounded, a simply connected domain that is not equal to the entire complex plane, you can always just transform it into some disk with a circle, and you're going to get, with appropriate considerations. The idea here is that like you can transform this into this and work on the circle instead. Yep.
How much if I transform that to the disk, invert it around the disk, and transform it back? Can I get information about what the function does on the outside?
No, because you're essentially still carrying the same. It's still the same set, right? So what you could do is you could try, if the function was actually analytic on the outside, you could take this set and flip it to the interior and solve the problem, and then flip back out. Yeah, you can do that. Yeah, so you get some region, you change it to a disk, you solve the problem here. Yep.
We just have an existence theorem about the LFT to the disk, right? We don't have a...
That's why, okay, so now what do engineers do? Yes, this is the fact that I can do this. What's the name of the theorem that says any region transforms into a disk? It's simply connected, not C. This is the Riemann, it's the Riemann mapping theorem, which is an existence theorem. Okay, so do you ever wonder about like why differential equations are always solved on disks and half planes and quarter planes and things that have easy ways of like conformally transforming from one to the other? Because those are the ones we know how to do. So this is an existence theorem that doesn't prescribe how we do it. So normally when we're solving these problems, we work on things where we can pull them back into disks, right? So, either you start with a setup where you've got some half-plane domain or quarter-plane domain and use a transform that's a well-known transform to get back to the disk, or you could cheat, right? So another way to do it is say, well, that original domain sucked because it's some blob. Maybe if I measure again, I can measure off some circle on the inside of it, right? That's a more physically motivated thing. Like, oh, well, I've got this blob and I've got this. Well, maybe I can just shave the outside off and make a circle instead. That's not a mathematical way of doing it. That's like a sort of practical consequences way of doing it. It's like, if only it was a circle.
Can you build the region out of circles?
Yeah, that's actually a consequence of analytic continuation, which we'll see. Is if you can start on a disk and then it's spread out to the rest of the domain, yeah, and uniquely. But anyway, so normally you just work on standard domains. Physical problems are normally set up on standard domains, and those standard domains have easy transforms to the disk, or at least well-known transforms to the disk. Okay, so the reason that you can do this is because you have linear fractional transforms. So LFTs do this. Theory of conformal maps. Now, what's the next type of problem that we want to consider? Well, what's the next most complicated thing I should prescribe at the boundary? Yeah. The derivative. I can tell everybody's taking an applied math class here. And what is it called when you prescribe the derivative at the boundary instead of prescribing the function at the boundary? It's a Neumann problem. Okay, so same setup. We're just going to start with, now, we're going to be given a domain A, and we're going to be given a boundary C. That is nice. And we're going to be given now not a function that prescribes the values at the boundary, but a function that gives the normal derivatives at the boundary instead, right? So we have a domain A, we have a C. C has a, now you're going to have to be sort of differentiable in some sense, because you're going to have to be able to have the derivative vary continuously. So the boundary, I'm sorry for those of you that didn't like your vector analysis here, is this, you need this to exist. So you need this to sort of vary smoothly, right? The direction of the normal vector needs to vary smoothly. And what you're going to do is you're going to prescribe the derivatives in the normal direction at the boundary.
Wait, so that varying smooth, that's a stronger condition in piecewise smooth, right?
No, because the piece you can do it piecewise. You're allowed to. It turns out to be the case that you're allowed to, as long as you can do this piecewise, you can still do it.
Okay, so as long as you only have a finite number of places.
A finite number of places where you have those sort of sharp changes, yeah. Because essentially this is still driven by an integral, and integrals don't care about isolated sets of singularities. So as long as you're piecewise varying, yeah. So no sharp corners. Right? Is the no infinitely sharp corners. No Weierstrass functions. If you guys know what a Weierstrass function is.
Oh god, is there a complex, like, version of that?
Yeah, somebody was Connor came into my office yesterday and we were talking about like, so in real calculus there are functions that are smooth but never have Taylor series anywhere, right? So it turns out that you can take that idea and you can do all kinds of horrible things with it, like sort of these locally Weierstrass things, that functions that can be even more than smooth and still not have Taylor expansions anywhere, which is atrocious. Anyway, so I need the direction of n to vary at least piecewise continuously. Okay, and so what we want to do is we want to say, well, what I'm looking for now is I want to prescribe the boundary derivatives. In the sense that I want to give you a function that describes the magnitude of the interior function in those directions. So now I'm going to give you a function u. So that is, I'm given a u, maybe a function. What does he use here so I can agree? Yeah. I want to find a u that is harmonic on A, and I want du dn to be specified. Oh, do you guys know what du dn is? It's the great. Yeah. Sorry, I just realized. For many of you, maybe it's been a while since you've seen vector calculus, or never if you've avoided 304. So by du dn, I mean the gradient of u dotted with n. So it's a scalar function, right? I give you a scalar function that describes the magnitude of the derivatives in the normal direction. Okay, so that is called a Neumann problem instead, and they're kind of annoying. So this is the Neumann problem. After von Neumann, who invented basically all of modern mathematics. So this turns out to be a bit more difficult, although it turns out to be the case that this cannot be specified arbitrarily. That if you demand that the function is harmonic, it puts serious restrictions on the behavior of the functions that you can do this with. Okay? And so it turns out to be the case that if such a u existed, then I think it's that the integral around the outside, the integral on gamma of du dn has to be 0. So this is one of the things about harmonic functions. It's kind of magic, right? Demanding that a function be harmonic is a serious assertion about how that function can behave. Remember, analytic functions are rigid as hell, really restricted in what they can do because of things like the maximum modulus principle. Harmonic functions have a maximum principle, which operates in the same way. Yep?
Sorry, what does that mean for like complex functions?
So what essentially this in complex functions is Gauss's theorem. right? Remember Gauss's theorem says that because you take the function, you've got Gauss's theorem that says if you have no holes in the interior, that you integrate around the boundary and you get 0. So this is essentially the same structure that Gauss's theorem carries with it. So this is the real harmonic version of complex. So I'll remind you that Gauss's theorem says that the integral around C of f of z dz is equal to 0 whenever f is analytic in the interior, right? The integral with C is a closed integral, and you integrate it around the boundary, and f was analytic on the inside, you got 0 out as the answer. So these are related to each other. This is actually a consequence of Green's theorem in the same way that this is a consequence of Green's theorem. You look skeptical.
No, I'm trying to draw pyramids.
Isn't that called the Cauchy-Gaursat theorem?
Cauchy-Gaussat, yeah. Well, yeah. We call it Cauchy's theorem, I think, right? Because I didn't give you the Gaursat proof, which is awful. I just I did the baby version of it, which is what Cauchy actually did, and Gaursat would like beef that theorem up. But yeah, fine. Cauchy-Gaursat. You are correct. Yep.
Is that also a statement about the flux of the gradient field across the boundary?
Essentially. Yeah. I mean, it's the divergence theorem.
Yeah.
So it turns out if you let x,
So
yeah, essentially if you let x be equal to the gradient of u to get a vector field,
yeah.
let x be equal to the gradient of u, and then plug that into the theorem that says that the integral around gamma of x dot n ds is equal to the integral around a of the divergence of x dx dy. If x is the vector field given by the gradient of u, the divergence of the gradient is nothing, right? Yeah. This is really secretly, if you take this and plug it into here, you end up integrating, this is the Laplacian. This is the integral around a of the Laplacian of u dx dy. But if that function is equal to 0 because the function is harmonic, this whole thing disappears. So when u is harmonic, the divergence theorem forces it to be the case that this integral is nothing, that's the same thing as asserting that this is, this is this. This integral is this integral, which is this integral, which is this integral, which is 0 when u is harmonic. So we're going to just start by assuming that this is true because we're looking for harmonic solutions. And so when we start probing the Neumann problem, this is going to be an assumption that we make about the structure at the boundary. So this is essentially, in complex analysis, the same as asking for a function to be analytic. We're saying, I'd like an analytic function, and that means I'm allowed to assume that Cauchy-Gaursat theorem holds. Okay, so I recognize that there's sort of been a lot of wind today and not a lot of actual computation, but the setup that we're using here is necessary to understand what the method is going to be when we actually start doing these problems. The big picture is we're going to construct, in the same way the Dirichlet problem has a standard solution given by the Poisson integral, and if I start with a different domain, I can transform it and solve and go back. There's a standard solution to the Neumann problem in a specific case. And what we can do is, which is a physically motivated standard solution, and then the idea is going to be to take different scenarios and transform them into the standard solution and then transform back. So we'll talk about vector fields and equipotentials and flow lines and potentials and all your favorite topics from vector fields next time.